Alright, the ideal gas equation, PV equals nRT, okay, summarizes the behavior of gases, okay, under low pressures. And for us to get a much better understanding of the behavior of gases, let's examine this equation carefully. And what we're going to do is we're going to try to hold as much of the variables here constant as possible. And we're just going to study two variables at a time. Okay, so you'll notice pressure, volume, number of moles, and temperature. Those are all variables. So a good way to understand an equation is to see what happens if you were to hold some of these variables constant and see what happens to the remaining two. Okay, so we're going to look at the situation here where you have a fixed amount of gas, so N is constant, and we're going to study what happens when the gas is at constant temperature. So temperature is constant. So R, of course, is a constant. So the whole thing on the right-hand side here is a constant. Okay, so your pressure times volume, we're going to let them vary, would be equal to a constant times a constant times a constant. So the whole thing on the hand side is just equal to a constant. Okay, now that behavior has been experimentally studied originally by Robert Boyle, and so the relationship between pressure and volume was in fact discovered by Robert Boyle. And basically, what does it say? Okay, it says that pressure, whenever the product of two things is a constant, then you say those two things are inversely proportional. So Boyle's law stated this based on experimental observations, and it's now, his work is now reflected in this, it's now incorporated into this ideal gas equation right here. Because if you were to hold the temperature of a fixed amount of gas constant, then you can see that pressure times volume is going to be a constant. Okay, so what does it mean when it's inversely proportional? Basically, what it says is if the pressure goes up, then the volume has to come down. Why is that? Well, if P times V is a constant, right? If I make my volume bigger, in order for the product to remain constant, I have to make my pressure smaller. Like if I double my volume, okay, and then I have to divide my pressure by 2 in order for the product to remain the same. Okay, so inversely proportional simply means if one goes up, the other one goes down by the same factor. So if one is doubled times 2, the other one must be divided by 2. If one is tripled, then the other one must be divided by 3 in order for the product to remain constant. Now, if you're going to plot pressure versus volume at a given temperature, you're going to get a graph that looks like this. Okay, so this would be like half of a hyperbola. It's like a plot of y equals 1 over x. Y versus x would look something like that. Okay, so it's going to have a shape that looks like a hyperbola. And every point here, if all of these data points are taken at the same temperature, then we say all of these data points, this entire curve would be what you would call an isotherm. Iso means the same, right? So this would be a plot of pressure versus volume at constant temperature. So this plot is called an isotherm. Okay, in an isotherm, then product of pressure and volume would be constant. So P1 times V1, so this P1 right here times V1 over there would be equal to P2 times V2. It will be equal to P3 times V3. Okay, so that's an important equation to realize that if you have an isotherm, the product of pressure times volume is going to be equal to a constant. So let's take a look at an example illustrating Boyle's law. Let's say you have a 25-liter sample of gas, initially at 1 atmosphere, and that gas happens to expand to 50 liters, same temperature, constant temperature. Calculate the final pressure. Well, you should be able to recognize this as pressure and volume being related at constant temperature. So you should be able to say right away that P1 V1 must be equal to P2 V2. P1 V1 is the before condition, before pressure and volume before the change occurred. P2 and V2 would be the pressure and volume after a change occurred. Remember, we said this is equal to nRT, right? nRT1, which is also the same as nRT2 because you have the same number of moles, the same temperature for this particular situation. So you can just solve for the final pressure. So let's call the P2 to be our final pressure. How do I solve for final pressure? P2 will just be P1 V1 divided by V2. Divide both sides by V2. So P1 is 1 atmosphere. V1 is our initial volume is 25 liters. And our final volume is 50 liters. And so that gives us 1 times 25 over 50.500. I have 1, 2, 3 sig figs, 1, 2, 3 sig figs, 1, 2, 3 sig figs. So I need 3 sig figs in my answer. 1, 2, 3. Okay? And liter cancels out, and my unit would be, of course, atmosphere. So that's your final pressure. So what essentially happened here? You doubled the volume from 25 to 50. What happened to your pressure? It got cut in half. It got divided by 2. So this is times 2. This is divided by 2. Pressure goes down, volume goes up by the same factor. That's Boyle's law. Okay? Let's take a look at this question right here. Which of these graphs illustrates Boyle's law? A, B, C, or D? Pressure goes up, volume goes down, right? But look at this plot right here. This is plotted versus 1 over volume on the x-axis. So you have to rewrite your equation. Pressure equal, remember PV is equal to a constant, right? Which is K. K being nRT, it's just a constant. Well, let's rearrange this so that you have P on one side. So P, divide both sides by volume. P equals K over V. Right? I divide both sides by volume. And I can rewrite my right-hand side. K over V is just the same thing as K times 1 over V. Okay? Plus 0. If I add 0 to something, it doesn't matter, right? Why am I doing it this way? Because I'm drawing here straight lines, graphs. And what's the equation for a straight line? Y equals mx plus b, right? So it appears I'm trying to plot pressure versus 1 over volume, so I want to be able to express my pressure in terms of 1 over volume, and this is how I do it. I rearrange my equation, so now if I put pressure on my y-axis, 1 over volume on my x-axis, then I can see here that y is equal to some constant k, so that's going to have to be my slope, right, plus another constant, which is non-existent, so that other constant must be 0, so that my y-intercept must be 0. So which of these graphs best represents Boyle's law? It's consistent with Boyle's law. You need a graph that's a straight line. When you plot pressure versus the inverse of volume, that's why it's called inverse proportionality, right? If you plot pressure versus the inverse of volume, you get a straight line with a slope equal to k. And what's k? What did we say K was? K is nRT. T is always a positive number, Kelvin temperature. R is a positive constant. N is the number of moles. It's always a positive number. So K here is a positive constant. So what does a positive slope mean? This can't be right. This is a negative slope, right? This is negative slope. This can't be right. This is a 0 slope. Horizontal line is a 0 slope. These two have positive slopes, but which one do you think is a better graph? A, because that's the one that goes to the origin, the y-intercept of 0. That's assuming, of course, the bottom left corner of your graph is the origin. Okay. When we do scientific graphs, we don't necessarily have the origin at the bottom left corner. But assuming that is the case, that you have origin at the bottom left corner, then A would be your best answer.